Indeed, today I would like to talk a little bit about PyTorch tensors because machine learning is becoming very popular. PyTorch is a machine learning library that has really exploded in popularity, mainly in academia, but more and more in industry as well. And the PyTorch tensor is the core object of this library. It's at the center of it. And I wanted to really focus this talk not on machine learning, but on this one object and try to really explain in a very thorough fashion what it is, why it exists, how to use it, how it works under the hood, etc., etc. So some aspects will be very introductory, basic operations on it. Some of it will actually be fairly advanced computer science topic about where things are stored in memory, but I was trying to really give an overview of this particular object in this talk. I want to have a little disclaimer before I get started. I stole quite a few drawings from this book to include in this talk, so I wanted to be very clear about that. And the first section on the PyTorch storage implementation of tensors also is highly influenced by this book. Also, a little logistical word. If you want to use tensors on your local machine, you'll have to install Python, of course, and then the PyTorch library. And all of these hyperlinks will lead you to additional information on installation. So later on, after the talk, I encourage you to follow these links if you want to dive deeper into the topic. And the link here will give you a clear explanation on how to install PyTorch depending on your OS, whether you have a GPU, etc. Then in addition, of course, if you want, you can use an IDE to run PyTorch, although this is absolutely not compulsory. If you want to use tensors on the Compute Canada clusters, you'll have, of course, to SSH into the remote terminal. And then you'll have to load the necessary Python module with a suitable version and the torch wheel. And this is the code that will get you there. And then once you've run this, you can run a job such as sbatch or salloc to play with tensors. Now, there are quite a lot of things that we will cover today. As I said, they're fairly diverse topics to try to really give a good overview of the subject. And the very first one, obviously, is, well, what is that Python object? So if we go back to machine learning, since the tensors were initially implemented for machine learning, artificial neural networks obviously do not process information directly. You don't actually feed a sentence or an image to a neural network. What you do feed is a whole lot of floating point numbers that represent, in the case of an image, for instance, pixel values, in the case of a sentence, the order of words, etc. So your information has to be transformed into floating point numbers. And then those point numbers are dealt with the network. And that's also numbers that you have at the end that are then reconverted into some kind of output that you are interested in. So we have a whole of numbers to deal with, and they need to be stored in some data structure. So the PyTorch tensor is really a Python object that holds a multi-dimensional array. A multi-dimensional array is some structure that holds elements of numbers, actually, of the same type, for instance, all float 32 or all float 64. So it's homogeneous. And you have a number of dimensions that allow to structure all these numbers and not have them in like a giant bag. Now, a lot of you will already be familiar with NumPy, and the ND array object in NumPy is exactly that. It's a multi-dimensional array. So why create a new object? Well, NumPy is already this amazing library, very integrated in the scientific Python ecosystem. It's very mature. It's a wonderful library. Why something else? Well, first of all, tensors can be run on accelerators. Accelerators are things such as GPUs, TPUs, there are others, but mostly, let's say, GPUs. So that's obviously a huge advantage. You cannot create a copy of an ND array on a GPU. Then NumPy wasn't created in the context of machine learning. And one really important thing in machine learning is to be able to keep track of the computation graphs of some of your operations so that you can do automatic differentiation, which means that the computer is itself capable to go back up the computation graphs, and this extra ability to keep track of computation is specific to tensor. And then finally, even though PyTorch can already run big machine learning models in a distributed fashion, the actual tensor object cannot run distributed computations at this point. But there are future plans for sharded tensors. So in the near future, you will be able to split tensors across various nodes in a cluster, for instance, and run in parallel across various nodes in a distributed fashion, massive operations on massive arrays. So this is yet to come, but all these are really great characteristics for machine learning, but also for other fields. So even though PyTorch was initially created really as a machine learning library, more and more people use it to do linear algebra on big data or other things. So don't think of PyTorch just as a machine learning library, but think of it as a library that provides this multi-dimensional array object that is very similar to NumPy and the array, as we will see, but as additional efficiency characteristics that are pretty interesting. So these are slides summarizing pretty much what I've explained. So now let's see what's happening under the hood. And this is something that I really didn't know much about and I thought was very interesting. PyTorch has this extremely efficient memory storage system under the hood. And this is one of the reasons, and some of it applies to NumPy and the arrays as well. This is one of the reasons why those libraries are so efficient. If you think of a classic collection in Python, such as a list or a tuple, so it's some grouping of objects. Each individual object is stored in some scattered place in memory, so they're all wherever, and they are all boxed. Boxed means that the primitive, the value, is stored somewhere in memory, but in addition to the primitive, you have a pointer to a reference to that primitive that allows you to access that particular object. Well, in the case of PyTorch tensors and NumPy and the arrays, the values are stored in a sequential grouped fashion in memory, making computations by the CPUs or a GPU that much easier. But in addition to that, the array itself or the tensor itself, so the Python object is boxed, but individual values aren't. So what that means is that if we take the case of 32-bit floats, for instance, each primitive, each value takes 4 bytes of memory and only 4 bytes. Then of course you have a little bit of memory that's taken by the boxing of the whole tensor, but you don't have that additional, I think it is 8 bytes of memory taken by the reference to individual box values. So you have this, the fact that values are not individually boxed, and even more important, the fact that the values are usually stored in contiguous memory blocks that make a NumPy ND array or a PyTorch tensor so much more efficient when it comes to memory than other type of Python collections, such as a list or a tuple, etc. So under the hood, the PyTorch tensors are stored as a torch storage instance, and this is actually a one-dimensional array. So no matter how many dimensions your tensor actually has, under the hood in storage it's stored as a one-dimensional array, which is extremely memory efficient. So the way to load the PyTorch library is import torch. So after you have done that, you can create a tensor, and we will look at these functions later. So don't worry about this particular line of code. What I am doing here is creating a tensor that is particularly easy to visualize. It goes from 0 to 9. It is made of floats. It is a two-dimensional tensor. It has how many elements does it have? 10 elements. Okay, so my tensor has 2 dimensions, but if I run, so my tensor is called T. If I run T storage, what I get is an output of the storage object, and it is one-dimensional. So this makes tensors extremely, it's a very efficient storage. Now, of course, in order, as a side note, you can even index the storage. For instance, the third element of storage is 3.0, and you can even modify it. If I replace the third element of storage by 10, you can see that the storage now has a 10 here. And if you were to print T, the actual tensor, obviously 10 would also be instead of 3 in the tensor. By modifying the storage, we are modifying the tensor, since the storage is the way the tensor is stored in memory. Now, obviously, to go from our unidimensional storage to our multidimensional tensor, we need something, we need additional element. And that element is stored in the form of metadata. There is the size, which is in NumPy parlance called the shape, very similar. So that's the number of elements in each dimension. Then there is the offset, which indicates the first element of the tensor in the storage. So when you first create a tensor, the offset, of course, is always going to be, I don't remember if it starts at 0 or 1, but like one of those. So the offset will only increase if you, for instance, index from a tensor. And then the stride establish the increment between each element. So bear with me, I'll explain those because I think it's interesting. Here at the bottom, you have an example of storage instance, so unidimensional. Here we have an actual tensor. So that's a two-dimensional tensor with 3 elements in each dimension. Now, okay, so you can see 5, 7, 4 are here, 1, 3, 2 are there. Okay, so how do we go from this storage to this tensor? Well, this storage starts with 6. So the tensor here was actually indexed from an initial larger tensor that has that value. So to go back to my uncertainty earlier, offset starts usually with 0. But here, because we don't start at the beginning of the storage, the offset is not 0, it's 1. So we start here. The size is 3 and 3. So that's the number of elements for each dimension. So, okay, so that's a 3 by 3 array. And the stride is 3, 1. 3 is how many elements we have to go over to go from one row to the next. So to go between 5 and 1, we need to go over 1, 2, 3. Okay, the stride is 3. The second element of the stride is how many elements you have to go over to go from one element in a column, like from one column to the next. Here, 5, 7, 5, 7, it's 1. So let's check it with a concrete example. Remember our T vector. So this is what our vector looked like. So it had 2 dimensions, 0, 1, 2, 3, 4, etc. to 9. Okay. So if I run T size, I get the size 2 by 5. And indeed, it had 2 dimensions. It had 2 rows and 5 columns. If I look at storage offset, it's 0. I haven't indexed this tensor from a larger tensor. So when you create a new tensor, the offset will always be 0. And the stride 5, 1 indicates, so 5, indeed, to go from one row to the next, we need to jump over 5 elements, and to go from one column to the other, we just jump to the next. So thanks to those 3 bits of metadata, which weigh really nothing in memory, 2, 5, 0, and 5, 1, our multidimensional tensor can be stored more efficiently in memory as a one-dimensional storage. And this is a terribly ugly graph that I tried to make to explain where all these things are, in case you want to brainstorm about it at your own pace. Now, something else that's advantageous about this system is that multiple tensors can use the same storage. And that saves a lot of memory because the metadata is extremely small and it's obviously a lot lighter than a whole new array. So if you do some indexing or transformation or transposition of a tensor, you'll get a new tensor. So the metadata will be different, but the storage object will be the same. So extremely memory efficient. Let's look at an example with transposing a 2-dimensional tensor. So transposing a matrix, basically. We can create a tensor here, 3, 1, 2, 4, 1, 7. Look at its size. So the size is 2, 3. Then we can transpose it with the T function, and we get a transposed matrix. And then we can look at the size again. Size is 3, 2. Okay. Now, what is interesting is that when we are transposing in 2 dimensions, what we are doing is that we are flipping the 2 elements of the stride around. Now, instead of having the stride being 3, 1, we have the stride that's 1, 3 in this example. And in our example, the stride will be flipped from our initial stride was 5, 1. It's going to be flipped to 1, 5. Now, you can also transpose in higher dimensions. Torch T is a shorthand for torch transpose 0, 1. So T only works for matrices. So it only works for tensors of 2 dimensions. But you can transpose tensors of any number of dimensions. You can transpose 2 dimensions in a tensor of any number of dimensions. So this shorthand is fairly limited. You'll have to use the transpose function for anything more than 2D. Oops, sorry, I'm going the wrong way. So now if we have a tensor made filled with zeros as float, now we have a tensor of 3 dimensions. The number of elements in those dimensions are 1, 2, and 3. But you can see that we have 3 opening brackets here. So we have 3 dimensions. It looks like superficially that we only have 2 dimensions because there's only 1 element in our first dimension, but this is really a 3-dimensional tensor. So its size is 1, 2, 3. The stride is 6, 3, 1. I can transpose along those two dimensions, the 0th dimension and the first dimension. And now I can see that the stride has flipped 2 elements, and I can transpose around the 0th and 2nd dimension, and you'll see that each time we're flipping 2 elements of the stride, same thing between the 1st and 2nd dimension. So that's how tensors are stored under the hood, and I think it's pretty cool. When you use tensors, you don't need to know that, but I think it's a neat system, and that's a neat implementation that's just great at the memory level. Now let's go into much more concrete things that you do need to know when you play with tensors. First of all, data types, D-type. Very similar to NumPy, except a big difference is that NumPy and the arrays use 64-bit as their default, so double floats. And because PyTorch was really created with like absolute utmost efficiency in mind, because neural networks are so demanding, the default type is 32-bit floating points. And that's really what you want for machine learning. This is totally sufficient for accuracy in the context of machine learning, and in a lot of other contexts as well. And it's going to be a lot faster. Just be aware of it when you transpose things, or if you use tensors in other contexts, if you want to have more accuracy at the detriment of efficiency, remember that the default is 32-bit. Maybe you want to change to 64 bits, depending on your applications. There are a number of D types, from Booleans to integers to floats. And again, the default is torch float, which is a single precision floating point number. Now, how do you know or change the type of elements in your tensors? Well, first of all, torch tensors will only output values of I forgot the word, characteristics. It's not the proper word, but elements, characteristics, the proper word will come to me in a second, is only created if it differs from the default. So if you create, for instance, a 2-dimensional tensor of random floats, you get an output without any information about the type. If D-type doesn't get printed, that means that D-type is float 32. It's the default. And that's true of any such things. Can't remember what they're called. But if you want to explicitly print D-type, you just have to run T D-type. Now, if you want to, right, and so if you create, if you want to, change the D-type of a tensor, there are various ways, but one way is to run type and then the D-type you want. And if you create a new tensor, here, for instance, I'm creating T2, which is T that I'm converting into float 64. Now, if I am printing T2, you can see that in the output, D-type is shown because it's not the default. And if I explicitly print it, I get float 64. I wanted to mention, I forgot at the beginning, if you have questions about anything, don't hesitate to type in the chat, or you can even unmute yourself and interrupt me. That would be totally fine. So now let's talk quickly about basic operations. I'll cover this very quickly because it's very, very similar to NumPy, and I'm sure most of you are familiar with NumPy. There are many ways to create a tensor. Here are some interesting functions. So torch tensor allows you to input individual values So you create the dimensions, add the values. This is a manual input method. Range in Python allows you to torch arrange does exactly the same as what range does in Python, but instead of having your range output as a series of individual objects, it creates a 1D tensor with a range in it. Linspace also creates a 1D tensor following a linear scale. Logspace is the same, but along a log scale. Rand creates random numbers on the uniform distribution, and we've already seen a few examples of that. Rand-n uses the normal distribution. Rand-perm creates a random permutation of integers that you give it. MT creates an uninitialized tensor that can be useful, for instance, at the start of a loop, or if you want to fill in a tensor by some function afterwards. Zeros, they're filled with 0, ones with 1, and I is the identity matrix. So a matrix that has ones following a diagonal, and that's for square tensors, square matrices. So let's look at a few examples quickly. If you use random functions such as torch rand, and if you want your results to be replicable, there is the torch manual seed that allows you to set a seed so that you would then be able to reproduce the exact same value. So you can pass any value in the manual seed. If you leave it empty, I believe it uses the time in second of your computer. So you can also leave this blank. So for instance, here, torch rand, I am creating a one-dimensional tensor with only one element of random floats here. If you want to extract the value of a one-element tensor, there is the item function. So if I use this item function, instead of having a tensor, I have an actual Python float here as an output. So that's a little function useful to know. So for machine learning, float32 is best. That's why PyTorch was implemented with float32 as the default. And yes, it absolutely will affect the speed of training. Everything will be much more efficient. So for machine learning, float32 will give you a precision that is totally adequate and tremendously speed up everything. So yes, for machine learning, float32. I recommend using float64 only if you have a very good reason to need this additional precision, and that wouldn't be in the field of machine learning. But maybe if you use tensors for linear algebra in the field of physics or other fields, maybe there are situations where you will need float64. But for machine learning, I assume that's what your question was about. Keep it the default. Yes, it will make a big difference. Because that's why they set it as the default. It's because it was the default that made the most sense with what tensors were initially created for. Okay, so now here, this is quite fun, I think, because we are increasing the number of dimensions, but we always have one element in each dimension. So there is a single value in all of those tensors, but you can see the growing number of dimensions. 1 dimension, 2, 3, 4, and you can see that the number of opening square brackets gives you a clear and direct indication of the number of dimensions. Here, I'm playing with size and dimensions here again, and you can look, if you're not familiar with NumPy and these kinds of multi-dimensional Python objects, you should play with it and look at this carefully. I don't have time to go over every single example, but those are characteristic examples that you should, at your own pace, think about, reproduce, and play with so that you get very familiar with those multi-dimensional arrays. So here, yes, I really encourage you to go over all these later on. So you can also create a tensor of a particular D type. You don't have to first create it with the default D type and then change it. You can set it directly at creation. You can also use the like function. For instance, I create T. Here is T. So it's a two-dimensional array filled with random floats. And then I can use zeros like T, and that will keep the size of T. So remember that the size means the number of dimensions and how many elements you have per dimensions, but fills it with 0. You can use it with ones, with rand n. So that can be a convenient function. And then all these other ways to create tensors. Now, you can also get some information on the tensor. We've already seen size, but there is also dim, which gives the number of dimension, and num-l, which gives the number of elements. Is it possible to change number of dimensions on a, yes, absolutely. Yeah. There are, view is one function that allows you to reshape matrices, and you can stack them. You can, yes, all these are totally possible operations. Absolutely, yeah. If you refer to the PyTorch documentations, you will see explanations of all these functions. But yes, you can do all of these standard manipulations without any difficulty. Yeah. Now, let's talk quickly about indexing. Something to keep in mind is that whenever there is a range, so a range is indicated with a column, the comma is implicit. So I'm creating a two-dimensional tensor here. This will output the entire tensor. This will output all of the elements. And it's the same as x square bracket column comma square bracket. So because I have a range, because I have a column, a comma is implied and I have all of the columns. So here I am getting the, and remember that in Python, indexing starts at 0. So here I have the third column, here I have the second row, here I have a particular element on the third row and fourth column. If you use -1, you get the last element. So here there is a column, so there is an implicit comma. If you add a comma after the column, you get the same result. So I am getting the last element, which is a tensor. Now, when you don't have a range, when you don't have a column, there is no implicit comma. So this is very different than if I were to add a comma. And here we are not indexing from a list of tensor. We are not indexing elements from a tensor anymore. We are indexing from a list of tensor because each dimension is a list of tensors in the previous dimension. So here, instead of getting a two-dimensional tensor, I am getting only a one-dimensional tensor. I'm losing one dimension here. Okay, I will let you go over these examples by yourself for the sake of speed, but you can also set the increments of indexing, etc., etc. Now, a word of caution about indexing. Indexing can be extremely useful. It's totally valid if you want to index some information as part of a tensor for, at the end of a computation, for instance. But you absolutely do not want to use indexing to run operations on a tensor element by element in a loop, because this would run the code in raw Python, and this would be utterly slow. And instead, you want to use vectorized operations. So let's talk about vectorized operations. And that's very similar to what NumPy and the array does. And there is a post that I am linking here that is really excellent to understand this and go over this slowly. So I really recommend you to read this post. But basically, NumPy is mostly written in C and PyTorch is written in C++. And those languages are a lot faster than raw Python. So when you run vectorized operations on arrays or tensors, you get an insane speed up compared to the same code that you would get in a loop using indexing of elements of your tensor. For instance, if you have a one-dimensional tensor of random values that's fairly large, if you want to calculate the sum of all of the elements of that tensor, in raw Python, you might think, okay, I'm just going to initialize the sum, and then I'm going to run a loop, and there we go. And I'm using here the indexing of each element of t to calculate my sum. Well, this is dreadfully slow. This is really not the way to go. Instead, you have a vectorized function that is just sum. And so this is going to run in C++. It's going to be extremely fast. It's going to be insanely more efficient. If we look at the results, we get the same output. So both methods are correct, but the difference in timing are just tremendous. So whenever you play with NumPy or PyTorch tensors, don't use indexing for operations, use vectorized operations. So all of these operations that I'm going to talk about now, they're all vectorized. They all run compiled, optimized C++ under the hood, and they're just very, very fast. So the view function allows to reshape tensors. There was a question about changing the number of dimensions of the tensor. The view function is what allows you to do that. You can reshape tensors, indeed. And as I mentioned earlier, you can also stack them, compile multiple tensors together. You can sum various tensors, and you're going to have the operation performed on all elements at corresponding locations. You can also use operations between a tensor and, for instance, a Python number. And in that case, the operation will be applied to every single element of the tensor. You have a number of reductions, such as the sum or the mean. So this is the example I took earlier. This is a much, much, much more efficient way to do a reduction here than doing it through a loop. You can, and I think that that's quite interesting. I encourage you to go over it, take your time and think about it, but you can do a reduction over specific dimensions. So if I just run sum, I'm going to get the sum of all the elements in my tensor. So I created the tensor of ones to make it easier, but so sum give me 24. Now, if you add the dimension on which you want to create the sum, you get tensors with the sum in the set dimension, and you can even create reduction over multiple dimensions. It's done over the first dimension and then done over the second dimension afterwards. Now, there is something else that is worth noting, and it's important for efficiency. It's in-place operations. Some operators, if you postfix them with an underscore, means that the tensor on which they are applied will be modified in place. So for instance, I have T1, that is the tensor 1, 2, T2 is 1, 1. If I do T1, add underscore T2, now I get, and I print T1, I get to 3. So now T1 has been transformed because the operation as the result of the operation has replaced the initial value of T1. You can also do it with 0, for instance, and now if you print T1, you get zeros. Now, why is this important? Well, you could do the same thing with reassignments, but there is a difference on how things are affected in memory. For instance, look at here, I create T1, so a very simple one-dimensional tensor with a single element. Okay, if I look at, so ID is a function that gives you the address of your element, your Python object in memory. Because we usually look at address in memory in an hexadecimal form, ID simply output a number, and that's fine, you can use that, but you can also pass that in the X function to have the address in a format we're more familiar with. So okay, I create T1, this is the T1 address in memory. Now, I ran on T1 the add_1. So if I print it, okay, it's worked. I've T1 now output 2. And if you look at the address in memory, you can notice that it's exactly the same. So that's in place operation. I could have done the same thing by doing a reassignment. If I write T1 equals T1 add 1 or T1 equals T1 plus 1, in both cases, I do the same operation as in the in-place operation. Each time I add 1. Okay, but if I look at the address in memory, you can see that because we are reassigning to T1, it's a different T1. It has the same name, but it's actually a different T1 because it is located somewhere else in memory. So it is a little bit less efficient because now we have created, we've had to change the address in memory. So in-place operations are slightly better. And it's interesting to see the difference between the two. So yeah, so view allow to reshape tensors, as I said, depending on, so of course you have to put values in view that make sense based on your initial tensor size, otherwise it's not going to work. And if you put -1 as one of the value, it will actually infer the size in that dimension based on the size in the other dimensions. So -1 is convenient if you don't want to brainstorm as to what value you need to put if you want a certain size in a particular dimension. Just a little comparison between, for instance, T, which we've already seen before, which will transpose the matrix, and view that will reshape your matrix. Those are not at all equivalent. You can see that view will change the size of your matrix in a totally different way. It's not a transposition. So just look at the difference and again, think about all that at your own time. All these dimensions take a little bit, at least for me, maybe some people are faster at processing all that, but for me, at first I needed to spend a little bit of time playing with it to familiarize myself with all those dimensions. So I think it's worth doing that peacefully. And you can also perform logical operations, just very, very similar. You can do it between two tensors, and then it's an element by element comparison that's being done with matching elements, or you can do it with a number, for instance, and then the test is applied to each element. So it's exactly the same processes, except it's logical instead of the mathematical operations, but the functioning is the same. Okay, so because NumPy is so prevalent so popular and so great and so well integrated in the scientific Python environment, maybe you are already doing things in NumPy. So what's really great is that there is a very easy interoperability between tensors and ND arrays. So even though now tensors are doing pretty much everything ND arrays was doing, that wasn't the case at first. But even if now that is the case, you might still prefer to play with ND arrays out of habit, or ND arrays might integrate better with some other library or whatever. So sometimes it's convenient to be able to convert back and forth. And what is great is that this conversion is extremely efficient because it is done without copy. And here, I want to explain this a little bit because it's a little confusing at first. So you can transform a tensor into an ND array. So the output format is a little bit different. We also know that the default D types are different, but otherwise things are very similar. Now, yeah, so mind the default of types. You can do the reverse operations very simply. Okay, but there's something that's worth thinking a little bit about. It's this idea of conversion without copy. T is my tensor. T and P is my ND array. So as far as Python is concerned, there are different types. So at the Python level, they cannot be the same object because they have different types. So if you look at the address in memory of T and P, they're actually different. So if you just look at Python, you might think like, oh, actually, no, it's not true that there was a conversion without copy. Like we have different objects. What is going on? But in fact, the underlying actual array that is written in C in memory is actually the same. And so if, for instance, you transform, like remember 0 underscore is a transformation in place. It will transform T in place, so at the same address in memory with zeros. If I do this and then I print T and P, here I'm not printing the tensor, I'm printing the NumPy ND array, you can see that I get zeros as well. So modifying the tensor with the 0 underscore actually modifies also the NumPy ND array. And that's true the other way around. So they are different objects as far as Python is concerned because they have different types. But in reality, the underlying array in C is the same in memory. So the transformation between the two is extremely efficient because it doesn't imply copying the data. It just transforms the little Python object that points to that data. So that's so the conversion is really easy. The code is very simple, and it's also extremely efficient. So that's they integrate with each other extremely well, which is really pretty great. Now there is one case where the conversion actually implies a copy. It's because NumPy only works on CPU. So if you want to convert a PyTorch tensor that you have allocated to a GPU, well, then that tensor will first have to be copied to the CPU, and then that one will be converted into an array without copy. So because of the NumPy limitation that it only runs on CPU, in that particular situation, you do have a copy, of course, but otherwise you don't. Okay, so while tensors were initially created for machine learning, because it's a really cool object and a very efficient object, people started to want to use them for linear algebra. And prior to PyTorch version 1.9, there were some linear algebra functionality, but they were a little limited. Now, with 1.9, so fairly recently, because the current version is 1.10, so that's a fairly recent development, all functions from NumPy linalg have actually been implemented. And of course, they're all implemented with ability to run on a GPU and with automatic differentiation. And there are also some additional functions over NumPy. So Torch is really now a tool that's fantastic for linear algebra. So don't necessarily think, oh, multi-dimensional array, linear algebra, NumPy. NumPy is great, but this is it is as great an option when it comes to functionality with accelerator and automatic differentiation support. So something worth actually thinking about. For instance, very quick example, we're running out of time, so I'll fly through it, but you can solve a system of linear equations by creating tensors with the left-hand side and tensor with the right-hand side. And to solve it, you have the Torch linalg solve, and it works just exactly like the linear algebra function in NumPy. The parallels are very strong, and so if you're familiar with linear algebra in NumPy, you'll be right at home. There are very slight differences. It's extremely similar. And then you can verify your result. And so there are a couple of other examples here that you can look at your own pace. You can also do matrix inversions, for instance. But here, a little word of caution also that there are situations where you might actually need to do a matrix inversion. But if your goal is to solve a system of linear equations, it's much, much, much faster. And it's also numerically more stable to solve that system directly than to compute the inverse of the matrix first. So think of the linear solve first. Don't jump to matrix inversions as part of that particular situation. So again, very similar to NumPy, and there are other linear algebra functions, the matrix product, etc., etc. Eigenvalues, eigenvectors, all very, very similar to NumPy. Okay, so I've said many times that one of the strong advantages of tensors is that they can run on accelerators such as GPUs. So let's see how that goes. Let's see how that works. Okay, attribute is the word I was looking for at the beginning. D-type is an attribute. Anything that gets printed if it doesn't have the default value is an attribute. So amongst those attributes, we've already seen D-type. Another one is the device. The device is the type of processor your tensor is stored on. So it can be CPU, it can be GPU with CUDA support. Now, and it's very recent development, it can be GPU with AMD's ROCm support, and it can be some XLA device, such as the cloud TPU with a particular package. So the initial implementation, the main one is GPU with CUDA support. It's being expanded now, but let's focus on the classic one with CUDA. So the values for the attributes on CPU is CPU. On GPU, whether it's CUDA or AMD, it's CUDA. And on XLA, it's this expression here. And for that TPU particular case, you need to import that package, and then you can use this. So so far, anytime we have created a tensor, we didn't have the device attribute printed because it was the default. And by default, the device is CPU. So everything that we have done so far was on the CPU because that's where it is by default. But you can create a tensor directly on a specific device by mentioning the value for that device. So here I'm creating a one-dimensional tensor of random values with device equals CUDA. Now, that tensor is stored on the GPU. The column 0 means that it's the first GPU. That's what will happen if you have a single GPU, for instance. Okay. You can also create a tensor on some device and then make a copy on another device. For instance, my T1 GPU, which I just created on the GPU, I can create a copy to the CPU. Yeah, so you can make copies. So you can create a device wherever you want. You can create a tensor wherever you want, and then you can make copies later on as well if you need. If you have multiple GPUs, you can also optionally specify which one a tensor should be created or copied on or copied to by, instead of using CUDA as the device value, CUDA column and then 0, 1, etc. So obviously, if you have only one GPU and you try to use CUDA column 1, you'll get an error message because that device doesn't exist. And there is an equivalent short form with CUDA and then between brackets if you want the particular GPU you want to send it to. So those are similar. Okay, and this does make a copy. So if you want to reduce the number of copies you are making, it's best obviously to create the tensor directly on the suitable device. But there are situations when you might need to move it around for some reason. Now, how much difference does the GPU make? So PyTorch has a built-in benchmark utility. I showed a little timing result at the very beginning of the talk when I was talking about vectorized operation, and I didn't mention it then because I wanted to keep that section simple, but what I used is the exact same thing that I'm using here. In Torch utils, there is the benchmark utility. So here I will create a matrix multiplication. I'll do the same matrix multiplication on CPU and on GPU. So I'm defining two tensors on the CPU to square 2D tensors, and the same thing on the GPU. So I have A and B that are on the CPU, A GPU, B GPU that are on the GPU. So same thing, except here I have device equals CUDA. And for all timing on this talk, I've been using my laptop and I have a dedicated GPU with 32 gig of RAM. So the benchmark utility from PyTorch allows you to run whatever expression you want to time a number of times. So it to get a more precise result and reduce random noise, you can run something, for instance, 100 times. That's a much more reliable benchmark. So I'm benchmarking the same A at B, so the matrix multiplication between A and B on CPU and on GPU. I'm running that 100 times, and here are my times. So on the CPU, it's 2.29 milliseconds. On the GPU, it's 108 microseconds. So if I calculate the speed up, I have a speed up of 21. So the computation was 21 times faster on the GPU. Now, if I do the same thing, but I make my tensors tenfold bigger in each dimension, the speed up is greater. Now it's 38. And the larger the computation, the greater the benefit will be between the CPU and the GPU. So for very large computations, the result is really big. And when we're talking of things that last a couple of days, well, that can be the difference between a day or two and several months. Now, a word about distributed operations. I mentioned that very briefly. It's still in the work. It's not an option yet, but I put some links to issues that are open on the GitHub repository of PyTorch that you can have a look at. There is planned for a sharded tensor primitive that you will be able to shard across nodes, and that way you'll be able to do massive linear algebra computations on massive tensors in across nodes in a very efficient fashion. So if this comes up soon enough, I'm very excited about it. I would love to do a follow-up webinar on this, but we'll see how fast that gets implemented. So I went over time, and I had to skip through some of the sections very rapidly because there was a lot of material in this webinar. If some of it went a little fast, all this material will remain available. I'm copying the link in the chat again here. The PDF version is a bit outdated, but if you give me half an hour, I will post the updated version. I encourage you to go over the sections peacefully and familiarize yourself with that object. But hopefully it has given you an overview of PyTorch tensors. And if you're into machine learning, hopefully it will have clarified some things that you might not have thought through while already using tensors. If you are not in the field of machine learning, if you are using NumPy on a regular basis, maybe you'll be interested to play with tensors and maybe try to get the benefit of GPU speedups or explore an alternative approach.